Shall I start the session?
Yes, sir.
Good afternoon all. So today we will solve the problem based on the activity coefficient. I think all of you have gone through the week 10 lectures which are available on SWIM portals. So question 1. A reasonably general expression for the vapor liquid phase equilibrium at low to moderate pressure is. So phi naught pi I yi p equal to gamma I xi f I superscript where by is the vapor fugacity coefficient is the phi. Phi is the vapor fugacity coefficient, gamma is the liquid activity coefficient, and f is the fugacity of the pure component. The ki value yi is equal to ki into xi is therefore in general a function of. So here are asked the questions. The ki is a function of. Option are given at temperature only, temperature and pressure only, temperature, pressure, and liquid composition, and both the temperature, pressures, liquid composition, and vapor composition. So, Ki is a vapor liquid distribution ratio, Yi into Xi, right? So, equal to gamma I I and P, right? Yeah, is the activity coefficients. So, activity coefficient is a function of temperature, pressure, and liquid composition, mole fraction, right? Similarly, this is the fugacity coefficient. Function, it is a function of temperature, pressure, and vapor composition, right? And if y not, it is a function of temperature and pressure, right? So here mentioned that at low pressures, at low pressure, fugacity coefficient is a function of temperature and pressure. Now from equation, Ki is a function of temperature, pressure, and liquid composition, right? I hope you got clear. Question number 2. At 60 degrees Celsius, vapor pressure of methanol and water are 84.562 kilopascal and 19.953 kilopascal respectively. An aqueous solution of methanol at 60 degrees Celsius exert a pressure of 39.223 kilopascal. The liquid phase and vapor phase mole fraction of methanol are 0.1686 and 0.5714 respectively. So we have to here activity coefficient of the methane. So here In this statement, temperature given, and then vapor pressure of methanol water given, total pressure given 39.223, and liquid phase and vapor phase of mole fraction given. Right. So we know the relation VLA between the ideal vapor mixtures and the non-ideal liquid solution. So Y I total pressure Xi gamma and even sat. Here methanol 1 and water. Okay. So here Y1 equal to 0.5714 and X1 0.1686, right? Now to calculate the activity coefficient of methanols, Yi into P to H1 into P1. All the value given here, put in this equation and calculate the activity coefficient. Right. 0.5714 to total is 39. 0.1686 vapor pressure of the methanol 84.562, right? That's 1.5. I'll have to got this value. Now move to the question number 3. A methanol water vapor liquid system is at equilibrium at 60 degrees Celsius and 60 kilopascals. The mole fraction of methanol in liquid 0.5 and in vapor 0.8. The vapor pressure of methanol and water at 60 degrees Celsius are 80 kilopascal and 20 kilopascal, assuming the vapor phase to be the ideal configuration. Right. Here, like consider one methanol 1, water is 2. The mole fraction in liquid means X1 equal to 0.5 Y1 0.85 and vapor pressure given of methanol waters. So here asks what is the activity coefficient of the water in the liquid phase. So here as per the waters. So similar relations means equation used Y I equal to gamma I X and P1 set. So for waters, we can type down W gamma water X water P. Right. So here X1 means X1 for the methanol, so X2 is 0.5. Y2 is equal to 5. Right. Okay, for water equal to XW with PW set. So here put the value for water 0.2 and P given here 80 kilo, sorry 60 kilopascal, and mole fraction of water liquid phase 0.5 into vapor pressure of water 60 degrees Celsius 20 kilopascals. Okay. So gamma is equal to 1.2. Right. Now second part, here all the excess gives a free energy. Right. So we know the relation G E by RG is equal to summation Xi. Right. So here is the binary solutions. So X M ln M. Right. First, we have to calculate here. This term is a unknown. So first we have to calculate activity coefficient of for methanol. So to calculate similarly in this equations. So gamma for methanol equal to Y in pressure to Xm into Pm. So 1.13. Now we got the activity coefficient for the water, then methanol, all the mole fraction given. Put all the value in this equation. We get the this G E by RT. Okay, here only also for the gives free energy. So here temperature gives 60 degrees Celsius. G by RT equal to 0.1523. Okay. So GE equal to 0.1523 into 8.314 into 60 degrees Celsius. Convert into the Kelvin. 273 plus 60. 421.6 joule per. All of you got this value?
Sir,
1 minute. Now moving to the question number 4. At 380 Kelvin at total pressure of 24.4 kilopascal, the composition of system ethanol and toluene denoted by 1 for ethanol, 2 for toluene at equilibrium. X1 is equal to 0.3 and 1 is equal to 0.634. The saturation pressure at a given temperature for pure component is P1 is equal to 23.08 kilopascal and P2 10.05 kilopascal respectively. Calculate the liquid phase activity coefficient, and second the value of G by RT for the liquid phase. Right. This is also same concept. So here given x1 and y1, so x2 equal to 1 minus x1 is the 0.7 and y2 0.36. Right. Also vapor pressure given. So calculate gamma equal to y1 p divided by x1 p1 set for volume y2 p divided by x2 p2 set. Put the value in this equation, you will get activity coefficient for ethanol and toluene. Right. So activity coefficient for ethanol is 2.23 2.2342, and for toluene 1.269. Right. Now then the second part, the value of G by RT. So G by RT is equal to summation Gx by ln. Right. For the binary solution, x1 1 2 gamma 2. Right. Put all the value, then you will get the G by RT. Right. So G by RT 0.408. Right. Question 5. Bar the binary mixture of A and B at 400 Kelvin and 1 atm. Which one of the following equilibrium state deviates significantly from the ideality? Right. So this is the equation given to calculate the vapor pressures. ln PE superscript set equal to power J6.2 minus 2758 divided by T. Here P is at is the vapor pressure of P, unit atm, T temperature, P is the partial pressures of P, unit atm, X mole fraction in liquid and Y mole fraction in vapors. So you have to check which of the option means which of the option given the deviate significantly from the ideality. Can someone tell the how would we solve this one? So at the ideal condition, gamma 1 is equal to 1, right? So if one of the option gamma not equal to 1, that is the deviate significantly from the ideality. So first calculate the vapor pressure of PE sat by these equations. So T put here, and then you will get A equal to 0.5 atm, right? Now gamma I xi pi set. So this is the uh, partial pressure. You can write down P, gamma I xi p1 set. Right. Now for component A, y A equal to gamma A into x A into P A set over P. Right. And P A partial pressure of component A equal to gamma A x A into P A. Right. This is the equation 1 and equation 2. Now check all the options, put in this equation and check the activity coefficients. So starting out from the option 1, so x is equal to 0.5 and y is equal to 0.25. So put this equation here, put this x value in this equation. Y is equal to 0.25 gamma, right? Now y is given 0.25, so you put 0.25 gamma, so gamma is equal to 1. So this is the ideal solution, right? This is now check option 2, option B, right? So x is equal to 0.5, so right. Now x is equal to 0.5, put in equation 2. So P A is equal to 0.25 gamma ATM, right? Now P is equal to given 0.25, so put here, so gamma A is equal to 1. This is also ideal solution, right? Take option C. So put x is equal to 0.5 in equation 2. So P is equal to 0.25 gamma. And put the PA value, P is equal to 0.5 in these equations. So gamma A is equal to 2. So this is not a not ideal solutions. So here gamma is not equal to the 1. So this is right, but we need to check the B option. So x A is equal to put in equation 1. So gamma is equal to 0.3 gamma. Put gamma is equal to 0.3 in this equation. Sorry, y is equal to 0.3 in this equation. So yeah, is equal to. So this is a right answer. Are got clear? Please make your mic mute. Question number 6. A binary mixture containing species 1 and 2 forms an azeotrophs at 105.4 degrees Celsius and 1.013 bar. Here is a mention the azotroph means a constant boiling point. Okay. The liquid phase of mole fraction of component 1x1 of this azotroph is 0.62, and at 105.4 degrees Celsius, the pure component vapor pressure of species 1 and 2 are 0.87 bar and 0.665 bar respectively. Assume that the vapor phase in an ideal gas mixture. The Vanillard constant A and B are given by this expression. Right. So we have to calculate the activity coefficient gamma 1 and gamma 2 under this condition. Then the van der Waals constant. Then we have to calculate A and B. Right. So we can calculate activity coefficient by using VLE between the ideal vapor mixture and non-ideal liquid mixtures relation. Y naught y1 into P equal to gamma 1 x1 and p1 square. So here is a azeotrope composition. So x1 equal to the y1, right? So gamma 1 equal to y1 p into p1 square. Right. So due to the azeotrope, so this get 1. And p1 there. Similarly for the second PCH divided by p2 square. Put the value. So gamma 1 equal to 1.154, gamma 2 is equal to 1.52, right? So option B are right. Now part 2, we have to calculate the Van Laar constant A and B. So we know the all the variables value, gamma 1, gamma 2, x1, x2, and put this all the value in equation. In this equation you will get the Van Laar constants. So A is a 1.12 and B is a 1.018. So options here right. I hope all of you clear. Question number 7. For a binary mixture at a constant temperature and pressure, which one of the following relation between the activity coefficient gamma 1 and mole fraction are the thermodynamically consistent? Right. So to check the thermodynamic consistency, gives them equations. Gamma 2 x1 will be 0, right? So now d ln gamma 2 dx1 equal to x1 divided by x2. So d ln gamma 1. So in option A given the ln gamma 1 equal to minus 1 plus twice x1 minus x1 square, and so here in means first option all the option are for the ln gamma 1 is the same, so you need to find out the expression for the ln gamma 2 using this equation, right? x2 dx1. This is equation 1. Now okay, this is equation 1. So now ln gamma 1 given by x1 x1 square, right? Now differentiate by dx1. So 2 minus 2x1 into 2 1 minus x1, so the 2 x2, right? Now put this value d ln gamma 1 divided by dx this in equation 1 and integrate it. D ln gamma 2 equal to minus 2 into twice x2 into dx2, right? Ln gamma 2 into twice x1 square by 2. So it cancels. So ln gamma 2 is equal to the minus x1 square. So option D is the right. All of you got clear? Question: at a binary liquid mixture is in equilibrium with its vapor at a temperature 300 Kelvin. The liquid mole fraction of x1 of species 1 is 0.4 and molar excess gives free energy 200 joule per mole. The value of universal gas constant 8.314 joule per mole Kelvin. And gamma 1 denotes the liquid phase activity coefficient of species 1. If ln gamma 1 equal to 0.09, then the value of ln2 up to the 2 digit after the decimal point is, right? So here x1 given, so x2 equal to 1 minus x1, so 0.6, right? So can G by RT equal to x1 ln gamma 1 plus x2 gamma 2, right? So ln gamma 1 given, so we have to calculate ln gamma 2. A excess gives free energy given, so R also known, sorry, R is a gas constants and T is a temperature also given here. 200 divided by 8.314 to 300. 0.4 into 0.09 plus 0.6 gamma 2. Ln gamma 2 equal to 0.0735. Right? It was simple. Huh? Moving to the question number 9. A binary liquid mixture consists of 1 and 2. Let gamma and X represent the activity coefficient and the mole fraction of the species respectively. Using a molar excess gives free energy model, ln gamma 1 versus x1 and ln gamma 2 versus x are plotted. A tangent drawn to the ln gamma 1 versus x1 curve at a mole fraction of x1 0.2 has a slope minus 1.728. The slope of the tangent to ln gamma 2 versus x1 curve at a same mole fraction each. So you know the Gibbs-Dom equations. X1 d ln gamma 1 d x1, x2 d ln gamma 2 d x1. Yeah. So this is a slope. So at 0.2 given. So I have to calculate this. Right. So put the value here. And x1 given x1 is equal to 0.2 and x2 is equal to 0.8. 0.2 minus 1.728 equal to minus x2 0.8 into d ln gamma 2 divided by dx1, right? Minus get cancels. So d ln gamma 2 dx1 into 0.432. So this is a slope of tangent drawn to the ln gamma 2 versus x1 curve at a same mole fraction, right? All of you got clear or not?
Yes, sir.
Question 10. A mole fraction and activity coefficient of component 1 in a binary liquid mixture are x1 and gamma 1. G is the excess molar Gibbs energy of the mixture. R is the inertial gas constant, and T is the absolute temperature of the mixture. Which of the following is always true? Option are given. Limit extend to 1, GE divided by RT equal to 0. Then limit extend to 1, G divided by RT equal to 0.5. And say limit extend to 1, gamma 1 equal to 0. And limit extend to 1, gamma 1 equal to the 0.5. So we know the relation G by RT equal to summation xi gamma ln gamma. Right. So for the binary mixture, G by RT equal to x1 gamma or ln gamma 1 plus x2 gamma 2, right? ln gamma 2. So as x tend to 1, so ln gamma 1 equal to the 0, right? Means for gamma equal to the 1, okay? And x 2 tends to 0, so gamma 2 infinity, right? Infinite value solution. So here check the all the graph for activity coefficient at 50 degrees per 6 binary liquid systems. Here when extend to the 1, so ln gamma tends to the 0, here also 0. Ln is also ln gamma tends to 0. And right, so GE the RT divided by 1 ln, this is a 0 plus x2 is 0 ln gamma to infinity, right? So 0. So G by RT, GE by RT equal to the 0, right? So this is one also one method to check this. And second method is, so you know the excess Gibbs energy equal to G by I, when x 1 tends to 1 and x tends to 0. At this condition, G is equal to almost GID. So means pure liquid component 1 only. So G is equal to 0. So limit x tends to 1, GE by RT equal to 0. So option A are the right. I hope you all are clear. Moving to the question number 11. The excess Gibbs free energy for the cyclohexane and phenols is given by G by RT equal to minus 2.1 into x1 and x2, where x1 and x2 are the mole fraction of the component when doing the liquid phase. The vapor pressure of the component at 417 Kelvin are P1 sat equal to 75.2 kilopascal and P2 sat 31.66 kilopascal. Now here asked derive the expression for the activity coefficient of each component as a function of the composition. Right. So how to derive you here activity function of composition, right? So we know the activity coefficient is related to the G by RT. So ln gamma is equal to T n G by RT to dni at pressure, temperature and energy. Here is the I. This is the equation 1. Now mole fraction for this is 1 totally, right? So G R RT here given minus 2.1 x1 in x2. So we can write down 2.1 n1 into n2 plus n1 plus n2. Yeah, right. Now multiply by systems by n minus 2.1 n1 into n2 equal to n1 plus n2, right? Now put this value in this equation and differentiate by the dni. Sorry, d is dni. So ln gamma 1 to minus 2.1 n2 n plus n2 minus n1 to n, yeah, right? So ln gamma 1 equal to minus 2.1, right? So n 2 square n square minus 2.1 x2 square, right? So similar calculations, ln gamma 2 is equal to minus 2.1 x1 square, right? Now so the same statement here we have to verify whether the expression derived in a year satisfy the Gibbs Doom equation. We have to verify. So Gibbs Doom equation summation xi d ln gamma equal to 0. For the binary solution, system d ln gamma 1 d x1 plus x2 d ln gamma 2 d x1 equal to 0. Right. This is the equation 1. ln gamma 1 to be derived minus 2.1 x2 square, right? 2.1 1 minus x1 square. Now differentiate with dx1. 4.2 1 minus x1, right? Similarly for ln gamma 2, 2.1 x1, okay. Differentiate with dx1 minus 4.2 x1. Now put this value in this equation. 4.2 1 minus x1 into x1 plus x2 4.2 x1, right? So write down h2 1 minus x1. So both the terms get cancels. 0 equal to 0. So this is the derived equation for the activity coefficient satisfy the Gibbs-Duby equation. All of you got clear or not? Now part C. Determine the equilibrium pressures P and vapor composition of the liquid phase composition at x1 equal to 0.1 and 417 Kelvin. Assume the vapor pressure to be ideal gas. We derived for the activity coefficient for the component 1 and 2. Minus 2.1 x square. So here x1 given, so x2. So calculate again 1 equal to 0. 2.2. 0.914. Similarly for calculate gamma 2 0.261, right? Now total pressure equal to y1 p, right? Is the partial pressure, means summation of partial pressures. So we know the relation is equal to x1 gamma 1 p1 sat, right? So put this value in this equations. Gamma 1 x1 p1 sat plus gamma 2 x2 p2 sat, right? So we know the gamma 1 gamma 2 value, x1 and x2, p1 p2. 6.95 kilobars. Right. Question number 12. Binary component 1 and 2 forms an azeotrophs at 130 degrees Celsius and x1 equal to 0.3. The liquid phase non-ideality is described by ln gamma 1 equal to the ax2 square and ln gamma 2 equal to ax1 square. where gamma 1 and gamma 2 are the activity coefficient and x1 and x2 are the liquid phase mole fraction. The both the component, the fugacidity coefficient are 0.9 at azeotropic composition. The saturated vapor pressure at 130 degrees Celsius for P1 sat equal to 70 bar and P2 sat equal to 30 bar. So the total pressure in bars for the above azeotropic system up to the decimal point. So here are the azeotropic pressure. So here vapor pressure given and also activity coefficient relation given. So we have to calculate the total pressures. So at azeotropic conditions, x1 equal to the x2 and x1 equal to y1 and x2 equal to the y2, right? Here given x1 equal to 0.3, x2 is equal to 0.7, right? So y1 is equal to 0.3 and y2 is equal to 0.7. Now y1 equal to y1 p equal to x1 gamma 1 p 1 z, right? Here is the fugacity coefficient given. So both the so I1 p equal to gamma 1 p1 set per second component I2 p equal to gamma 2 p2 set. Now take ratio gamma 2 by gamma 1 equal to p1 set and p2 set. So gamma it cancels, right? But here given ln gamma was equal to ax 2 square. So you can write down e is to the power a x1 square a is to the power a x2 square, right, equal to p1 square divided by p2, right? X1 square minus x2 square, right, equal to p1 square by p2, right? So we know the x1 and x2, p1 and p2 will get a constant value of ea equal to minus 2.11 p2. Now you know the value of constant a. Now calculate the ln gamma 2, sorry the gamma 2 value by using these equations. So gamma 1 equal to Use the equation 1 to calculate the total pressures. So first calculate the gamma 1 value 0.3542. Now P is equal to gamma 1 P1 that for pressure equal to the gamma 1 P1 set is equal to I1. So we can use the both equation to calculate the pressures. So P is equal to 27.5489. Moving to the question number 13. The molar excess gives free energy G with superscript D of liquid mixture of E and A is given this equation given, where X and XB are the mole fraction of E and B respectively. Universal gas constant R is equal to 8.314 joule per mole per Kelvin. T is the temperature in Kelvin. C1 and C2 are temperature dependent parameters. At 100 Kelvin, C1 is equal to 0.45 and C2 equal to minus 0.018. If gamma A and gamma B are the activity coefficient of A and B respectively, the value of integration 0 to 1 ln gamma E divided by gamma B to Tx at 300 Kelvin and 1 bar. So you have to calculate this value. So this equation given first. Now put the value C1 and C1 and C2 here, right? Mole fraction not given. So G by RT, put the value in this equation and replace XB by 1 minus X in this also. X A X cell 0.468 minus 0.0366. Q by RT 0.036 x a cube minus 0.504 x a square plus 0.468 x. Right. Now differentiate by dx a 0.108 x square minus 1 8 x a plus 0.468. Right. Now there is one relation T G E by RT divided by dxa equal to ln gamma A divided by gamma B, right? Now we know the this value. Now this equation multiply by dx on both side and then integrate. हम limit 0 to 1 ln is equal to dxa equal to sorry, we don't have to multiply dx. Yeah. So dg by rt equal to ln gamma A gamma b dx. Now integrate 0 to 1 0 to 1 ln gamma A gamma b 0 to 1 dx equal to so 0 point integrate this 0.036 minus 504 0.504 plus 0.468, right? It's 0. So 0.036 468 0. So the value of integration 0 to 1 ln gamma A divided by gamma B into dx equal to 0. All of that clear or not? Question number 14. The Van-Laak activity coefficient model for the binary mixture is given by the form. So, here gamma 1 1.40, gamma 2 1.25, x1 is 0.25, x2 0.75. Determine the constant A with superscript star and B with superscript star. Option are given here. So write down A star is equal to here and B star equal to the B. So ln gamma 1 equal to A and B x1 x1 for ln2 equal to B 1 plus B by A x2 by x1, right? So you can write down this Vx2 Ax1 It should be square. Then learn. It should be square. X1 will be x2 by x1. Now take a ratio ln gamma 1 divided by ln gamma 2 equal to a equal to b square x2 square b into a square into x1 square. So b into a is equal to x2 square x1 square, right? Now x1 ln gamma 1 x2 ln gamma 2 equal to b by a x2 by x1, right? x2 ln gamma 2 x1 ln gamma 1 equal to a x1 b x2, right? This is the equation 3 and 4, right? Now ln gamma 1 equal to a 1 plus so put this value in equation 1 and 2. So x2 ln gamma 2 x1 ln gamma 2, okay, or ln gamma 2 is equal to b 1 plus x1 ln x1 gamma 1 by x2 ln gamma 2, right? Now gamma 1 value given and x1 and x2 given, and calculate the NB. So a is equal to 3 and b is equal to 0.5. So it's equal to a star and b star. So 3 and 0.5 is equal to 3. So option B is the right. I hope all of you clear this one. So I covered all the question based on the activity coefficients. So if you have any doubt, please ask. Thank you all. I conclude today's session. We will meet on next Saturday and next chapter at same times. Thank you.